Hello, science educators. Bill Nye here, ready to explore the fascinating world of physics with you. Today, we're diving into circular motion, a fundamental concept that governs the movement of countless objects around us. It's a concept that explains everything from the simple spinning of wheels on a car to the grand, sweeping orbits of planets around the sun in our solar system. Circular motion, at its core, is simply an object moving along a circular path, tracing a perfect or near-perfect circle as it travels. This movement can occur either at a constant, unchanging speed or with a speed that's constantly changing, accelerating or decelerating as it goes. But what is the secret ingredient? What unseen force keeps an object faithfully moving in a circle, preventing it from flying off in a straight line? There's always a force, known as centripetal force, constantly pulling it inward, towards the center of the circle. Think about the rotation of car wheels as they grip the road, the whirling motion of helicopter blades slicing through the air, or the majestic orbits of satellites gracefully circling the Earth. They all rely on the principles of circular motion to function. The underlying principle at play here is Newton's first law of motion, also known as the law of inertia. It states that objects naturally want to move in a straight line, maintaining their velocity unless acted upon by an external force. But in circular motion, that centripetal force, must constantly pull them inward, deviating them from their natural straight path. Without that inward pulling force, the object, obeying Newton's first law, would indeed fly off in a straight line, tangent to the circle. Therefore, circular motion can be visualized as a continuous tug-of-war, a delicate balance between inertia's tendency to move straight and the centripetal force relentlessly pulling toward the center. Our job as educators is to illuminate this invisible dance, to make the abstract concepts of force and motion visible and understandable to our students. So let's get started on this exciting journey of discovery, because science, without a doubt, is undeniably cool. Let's delve deeper and get to the very heart of circular motion, specifically, the concepts of acceleration and force that govern it. Even if an object maintains a constant speed as it moves in a circle, its direction is constantly changing. Therefore, it's accelerating. This might seem counterintuitive at first, but it's a fundamental aspect of circular motion. This acceleration is called centripetal acceleration, and it's a crucial concept to understand. The key characteristic of centripetal acceleration is that it's always pointing directly toward the center of the circle. Newton's second law of motion tells us that force equals mass times acceleration, a fundamental relationship in physics. Therefore, a net force, the centripetal force, must constantly pull the object inward towards the center of the circular path. It's important to remember that centripetal force isn't a new fundamental force of nature. It's simply the name we give to whatever force is responsible for keeping the object constrained on its circular path, whether that's gravity, tension in a rope, or friction between surfaces. Now imagine what would happen without this centripetal force. The object's inertia, its tendency to resist changes in motion, would cause it to fly off in a straight line. Remember, at any point in the circular path, the velocity is always tangent to the circle, indicating the instantaneous direction of motion. In contrast, the acceleration and the net force always point towards the center of the circle. These fundamental ideas explain why you experience the sensation of being pushed outward when you're in a car turning a corner, and they also explain why the moon is able to maintain its orbit around the Earth. Ultimately, it's all about that constant center-seeking pull that governs circular motion. End of scene. Let's dive into the world around us and see circular motion in action. It's not just a concept in textbooks, it's a fundamental part of our everyday lives. We can observe it in many different scenarios, from simple experiments to grand cosmic events. Consider this classic demonstration. Swing a bucket of water in a circle. As you swing, your arm provides the centripetal force, constantly pulling the bucket inward and keeping the water securely inside, even when the bucket is upside down at the top of its arc. This force counteracts the water's tendency to move in a straight line. Now, think about driving. When a car turns a corner, friction between the tires and the road supplies the necessary centripetal force, allowing the car to change direction and follow a curved path. However, if there's not enough friction, perhaps due to ice or a slippery surface, the car loses its grip and skids straight ahead, unable to complete the turn. Zooming out to a cosmic scale, we see that gravity acts as the centripetal force, perpetually keeping Earth and all the other planets in their orbits around the Sun. It's a never-ending dance through space. In each of these cases, whether it's a bucket of water, a car, or a planet, the object inherently wants to move in a straight line, obeying Newton's first law of motion. However, a force continuously pulls it inward, constantly changing its direction and forcing it to trace a circular path. Whether it's tension in a rope, friction between surfaces, or the universal force of gravity, the underlying principle remains the same. These examples vividly show students that physics isn't just abstract theory confined to textbooks and classrooms. Instead, it's a living, breathing reality that's all around us, influencing everything from the simple joy of playground swings to the majestic orbits of planets in space. By carefully breaking down these seemingly complex scenarios, we can reveal the elegant and universal rules that govern every spin, turn, and orbit in the universe. Circular motion is everywhere, and teaching it can be hands-on and fun. Classic demos, like swinging a bucket or spinning a stopper on a string, let students feel centripetal force in action. Changing speed or string length shows how force and acceleration are connected. Relate it to real-life banked racetracks, use angled roads to help friction provide more centripetal force. Or ask, how fast must a satellite go to stay in orbit? Now physics becomes engineering and astronomy. Our goal is to make these invisible forces visible and intuitive. Circular motion brings Newton's laws to life in 2 dimensions. With clear examples and hands-on activities, we empower students to see the forces shaping their world. That's what science education is all about.